Chapter 7, Section 7 deals with the topic of power. But before we get into that, let's do a quick review of where we are in Chapter 7. We started out Chapter 7 by developing the work energy theorem, which says the work done by all forces is equal to the change in kinetic energy. Now, your textbook doesn't use this terminology. They label this as work done by the net force. Let me show you where that comes from. Say we have a problem of a block with four forces on it. Now, normally we would call these forces gravity, normal force, friction. But to keep it general, let's label this force 1 through force 4. Now, Newton's second law says that if we add up all the forces, it'll equal mass times acceleration. And this is a vector equation. So the forces have to be added as vectors. Now, if I add those forces as vectors, I can replace those forces with what they add up to. And that's what your textbook calls the net force. So they say the work done by the net force is equal to change in kinetic energy. That's the same thing as saying the work done by all the forces is equal to change in kinetic energy. So after coming up with the work energy theorem, we define these terms conservative and non-conservative. We said that forces can be one of two types, either conservative or non-conservative. Examples of conservative forces are the force of gravity, the force of springs. Examples of non-conservative forces are friction, people pushing on things, normal forces. And actually most forces are non-conservative forces. There are only a few special types of forces that are conservative forces. The thing that makes them a conservative force is the fact that you can define a potential energy function for them. So, for example, gravity, we can define mgh as the potential energy function. Or for a spring force, we can define 1/2 kx squared as the potential energy function. Contrary to that, non-conservative forces have no potential energy functions. You can't define a potential energy function for a non-conservative force. That's what we mean by a non-conservative force. Now, since we can divide forces up into conservative and non-conservative, we can take our work energy theorem and say that the work done by all forces is equal to the work done by conservative forces plus the work done by non-conservative forces. And that will equal the change in kinetic energy. Now, because the conservative forces can have potential energy functions associated with those, we can take those potential energy functions, move them over to the other side of the equation, and our work energy theorem now becomes the work done by non-conservative forces is equal to the change in kinetic energy plus the change in potential energy. And this is what we define as the total energy, kinetic plus potential. Now, given this equation, if there are no non-conservative forces, or at least if there is no work done by the non-conservative forces, then the left-hand side is 0, and we have energy conservation, that the initial kinetic energy plus potential energy is equal to the final kinetic energy plus potential energy. This is equation 748 out of your textbook. In the case where work is done by non-conservative forces, so if we have a problem where there's friction, for example, then our work energy theorem, or our energy equation, turns into this, where we have an initial total energy, a kinetic energy plus a potential energy, plus the work done by non-conservative forces will equal the final total energy, final kinetic plus the final potential. Now, in some problems, there will be additional forms of energy. And so your textbook distinguishes these by throwing in another term that they call OE, or other energy. And so if I start out with an initial total energy and I have non-conservative forces doing work, and there are other energies in the problem, if I add all those together, it will equal the final kinetic energy plus potential energy plus whatever these other forms are in their final state. Examples of other forms of energy are electrical. You can have a motor lifting a weight, and there will be electrical energy going into the system. You can have chemical sources of energy. For example, eating food, taking in calories. Your body converts those calories into energy. Muscles contract and allow you to do work, to move objects, slide boxes, lift weights. You can have solar energy in a problem. Radiation from the sun hits a solar panel, generates electricity. That can add energy to a system. Nuclear energy, you can have a nuclear process heating up water, causes it to boil, which turns turbines, generates electricity. Thermal energy is another example of a different form of energy. In the case of diesel engines, a fuel-air mixture gets compressed through a mechanical process, and that greatly increases its temperature. Then that fuel-air mixture ignites or explodes. Then in that case you have chemical energy turning into, again, mechanical energy, pushing the piston back up. Coming back to the idea of power, let's take a look at figure 724 from page 265 out of your textbook. This is a figure that's used in example 711, which is analyzing the problem of a girl running upstairs. She starts with an initial velocity of 0 and ends with a final velocity that is non-zero. But I want to look at this in a slightly different context. Let's assume that instead of starting at 0, she starts with an initial velocity which is equal to her final velocity. So during the process of running up the stairs, she does not speed up or slow down. She's running at a constant speed. Now, if you imagine this process of running up the stairs at a constant speed, you know it takes a certain amount of effort, a certain amount of work. Just as we use terms like work and energy in our everyday lives, those terms have a relationship to their technical definitions in physics. Power is another concept that we use in everyday life, but also has a technical definition in physics. From experience, you know that it takes a certain amount of effort to go up the stairs. But you also know that the faster you go, the more effort you have to exert. It's true, though, that the work done in going up the stairs is going to equal the change in kinetic energy plus the change in potential energy. And if we don't change the kinetic energy, if we keep the same speed throughout the process of running up the stairs, then the work done will be equal to just the change in potential energy, which in this case, our change in potential energy is just mgh. So the work done in going up the stairs is a fixed quantity, and it does not matter how fast she goes up the stairs. So if she walks slowly up the stairs, she does work mgh. If she runs up the stairs, she does work mgh. She does the same amount of work in both cases. But you know from experience that it takes more effort to run up the stairs than it does to walk up the stairs. And that leads us to the idea of power. There's another useful quantity to define, which involves how quickly something is done. And so we define power as work divided by time, or work per time. So power is defined as a work or a change in energy per time. It has units of watts, named after the scientist James Watt, and 1 watt is 1 joule per second.